In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
Solar wind, cosmic rays, and UV radiation. They're forces from outer space that affect our lives every day. And most of us don't even know it. From skin cancer to lost transmissions, these cosmic phenomena can cause us harm. Yet they can also dazzle us with the beauty of an aurora and the brilliance of a shooting star. Get ready for the wonders and the dangers of cosmic phenomena.
Just magnificent. It's full of dynamic motion. It is changing every time you look at it. It's the biggest thing you've ever seen.
It's just a beautiful sight, kind of completely unlike anything we know. It's so weird to see the sky behaving in such a fashion.
You see these flittering lights in the sky. They're changing with time in beautiful and wondrous ways. It's really an out-of-this-world experience.
Once in everyone's lifetime, they should see one of the most spectacular psychedelic light shows that nature gives us, and that's the Aurora Borealis.
It was named after Aurora, the Roman goddess of dawn, and the Greek god of the north wind, Boreas. In the southern hemisphere, it's known as the Aurora Australis. Way before they dazzled astronomers, auroras amazed the first people who saw them in the polar regions. To ancient Scandinavians, only an equally amazing explanation for the dazzling displays would do. They believed a giant fox in the sky, swishing its tail, caused the northern lights to appear.
I like that explanation because it is not that far from the truth. The aurora is an electric phenomena, and when a fox swishes its tail around, you deal with static electricity, and you may actually make sparks and an aurora-like phenomenon. If you want to know how an aurora comes about, you have to start at the sun.
The sun. It's not only our source of light, but also energy. Lots of it. The sun emits a steady stream of charged particles known as solar wind, a cosmic force sometimes intensified by a coronal mass ejection.
Solar wind can cause some glow in the upper atmosphere nearly any time of the year. But occasionally the sun has these tremendous outbursts. They're called solar flares or coronal mass ejections. And then a whole stream of charged particles comes to the Earth at about the same time, a whole bundle, a whole bunch of them. And that then causes a lot brighter auroral phenomena.
Traveling at speeds of up to 750 miles per second, it takes solar wind about 2 days to reach the Earth's magnetic field. As the energized particles stream along the magnetic field towards the poles, they excite gases in the Earth's upper atmosphere and produce the colored lights that make up the aurora.
When the energetic particles hit the upper atmosphere, they first encounter atomic oxygen, which gives us the red line emission and the green line emission, the most prevalent emission in aurora. Further down, you can encounter molecular nitrogen, and that gives us, if the aurora is very intense, at the bottom edge of the green curtain, a purple lower border.
Charged particles interacting with excitable gases to produce bright colors. the aurora functions much like a neon sign.
Neon works by, you take a little bit of a rare gas and put it in a tube at very low pressure, and then you apply anywhere from 3,000 or 4,000 volts to maybe 15,000 volts. We'll ionize the gas and excite it into giving off its characteristic color. The gases that are available for all neon signs are xenon, which is a real pale blue, helium, which is a kind of a peach color, krypton, which is a silver color, it's not a planet, and argon, which is a lavender, and neon, which is the brightest, especially on a rainy night.
Auroras, too, are best viewed at night, especially during winter in polar regions, when the nights are as long as they are dark. Depending on the amount of solar activity, auroras can last from a few minutes to several days, and be seen not only near the poles, but also on rare occasions at lower latitudes.
Just a few years ago, in 2003, we had what we call a century storm, the biggest magnetic storm in 100 years. It was a big aurora associated with that. People in Washington, D.C. could see the aurora, in the Mediterranean. Everywhere you don't see aurora very often. And one of the biggest that we know of was in the middle of the 19th century, that caused aurora that was seen from Hawaii and other places in the South Pacific. And it is the biggest aurora on record that we know of.
Auroras can even be seen beyond Earth. The solar wind goes out in all directions, reaching further than the planets. Jupiter and Saturn have huge magnetic fields, bigger than our own, which make for especially large and intense auroras. But regardless of where they're seen, how long their duration, or intense their display, auroras usually appear as glowing curtains with folds or striations that change constantly. Time-lapse photography speeds up the effect. These signature features add to the aurora's beauty and mystery.
The shape of the curtains of the aurora and the motion within these shapes, these rays and curls and wiggles and spirals and all of that, is a subject of active research. We don't really understand all of that yet.
Adding to its mystery are reports that the aurora can not only be seen, but also heard.
The aurora is at 100 or 60-mile altitude, and the sound would take several minutes to come to us before we can hear it, and yet people report that they hear the sound simultaneously when they see the aurora. So there must be some unknown mechanism that makes people think they hear, or makes them hear something that may be associated with aurora. Nobody has an explanation for that, and some people are trying to find out what it is.
Auroras by themselves pose no threat to humans. But the increased solar activity associated with them can generate about 1 million megawatts of electricity and cause us problems in other ways, such as disruptions with power lines.
It's not the aurora itself that's causing the problem with the power lines. It's the charged particles that have come in from the sun, and they cause the damage and the interference to the power lines. That's an important distinction to make.
With that increased activity and movement of electrically charged particles that give rise to aurorae, they also interact with anything else that has an electric or magnetic field associated with it. So those charged particles are disrupting, whether it's power lines or electronics and satellites or cell phone coverage, anything where you need electric and magnetic fields to run your apparatus will get disrupted at the same time that aurorae are taking place.
So the static on your radio, the blip on your TV screen, that dropped cell phone call, or even a blackout like the one that hit Quebec, Canada in 1989, could just be blunt reminders of the Earth's humble place in the solar system.
The Earth is just a planet going around the sun, and the sun has an atmosphere that extends well beyond the Earth. So the Earth is actually living in the outer atmosphere of the sun. What the sun does, when it varies the outer atmosphere, it affects the Earth. So it affects the systems, the technological systems that we depend on.
Though auroras are a mere side effect of the sun's interaction with the Earth, they can enlighten us about the cosmos.
The aurora is a good indicator of how the upper atmosphere and the magnetic field of the Earth interact with the solar wind, which eventually comes from the sun. So we can use the aurora as a study object, essentially, that nature provides for us to understand better what goes on in the rest of the universe.
The auroras are one of the measures of solar activity. So in tracing history back from the present day, back to the 10th century or the 8th century or even before, the auroras are one thing that you can use as a measure of solar activity. So the sun has a 22-year cycle of activity. Every 11 years it becomes more active and then it reverses its polarity and comes back. But you can trace this back in time, and the auroras are one of the best markers of that.
While auroras are most often viewed in the polar regions, there are other dazzling cosmic phenomena that can be seen anywhere. They're called shooting stars.
When we see shooting stars, they look like stars that fell onto the planet Earth. But that can't be right. Stars are much bigger than the planet Earth. If you really had a shooting star, it would gobble up the Earth within a fraction of a second.
So if it's not a star, then what is it?
It's just a little tiny pebble, like a grain of sand from outer space, zipping through our atmosphere and colliding with the molecules and atoms in the atmosphere and causing them to glow. So it's not a star at all, nothing even remotely similar to a star.
These glowing pebbles are better known as meteors.
Most burn up in the atmosphere. Some, if they're large enough, can make it all the way through the atmosphere and drop to the Earth. And we find a rock called a meteorite, and that is really the same phenomenon.
The pebbles and dust particles that make up meteors are leftovers from the formation of our solar system. Mostly scattered debris from previous generations of stars.
Many of them also come from the asteroid belt. Between Mars and Jupiter, there's a whole bunch of rocks floating around, and occasionally they hit each other and shatter, and these little grains go flying around in the solar system, and some of them eventually intersect Earth's atmosphere.
At certain times of the year, a large number of meteors streak across the sky. These events are called meteor showers. They occur when the Earth passes through a trail of debris, bits of ice and grit left by a comet as it orbits the sun.
When you look at a meteor shower, the meteors, or shooting stars, appear to emanate from a single point in the sky, the radiant. They radiate away from there. But really, the little bits of ice and rock that make up the meteors are traveling in a bundle along essentially parallel paths through space. They're not diverging from a single point. They only appear to be spreading apart because of the perspective, the fact that you're looking at them from a great distance and they seem to come from a vanishing point. You can see the exact same thing in this hallway. The walls are parallel to one another, the ceiling is parallel to the floor, the lines of intersection between the floor and the wall and the ceiling and the wall are parallel to one another, but they all appear to converge far down the hallway there. They come from a vanishing point because of the perspective. And if you go back to the meteors, in a similar way, the particles are all traveling parallel to one another, but only appear to diverge from the radiant because of perspective.
Meteor showers are named after the constellations from where they appear to emanate. even though they have nothing to do with the stars in the constellation. The Leonid meteor showers, named after the constellation Leo, are some of the most brilliant on record. The one in 1833, by some accounts, had as many as 200,000 meteors per hour. Some observers thought the world was coming to an end. But in some ways, it was just the beginning. In recent years, new cosmic phenomena have been discovered that are even more dazzling than meteor showers. They emit brilliant colors at lightning-quick speed. Blink and you'll miss them. But we got them. Cosmic rays sound like something from a sci-fi movie. An invisible force from outer space that can cause changes in weather and much more. But cosmic rays are real, even if the term is a misnomer.
Cosmic rays are particles. They're not rays. They were originally thought that maybe they were a light phenomenon, but they're not. They're particles. They're made of the same elements that the sun and earth and everything in the universe is made of.
Cosmic rays are any radiation that comes from outer space. So there's lots of different sources. The main ones are the sun, because it accelerates a lot of energetic particles. And the other one is stars and galaxies, black holes, neutron stars, everything else.
Most cosmic rays are not super energetic by Earth standards, but the most energetic ones would be the equivalent of like a well-hit tennis ball hitting you in the head. That would not feel good. But many of them are like a little pea from a pea shooter impinging upon you, or even less energy than that.
The Earth's atmosphere protects us from most cosmic rays. But those high-energy particles that do manage to penetrate the atmosphere are potent enough to make an impact on all living organisms.
They can cause mutations in the DNA. In fact, that's one of the canonical explanations for why there's a genetic drift among species, because cosmic rays cause the DNA to change a little bit, and that leads to variations in species of animals.
Some of these mutations influence evolution for the better.
What is evolution? It's based on the idea that your genes can change ever so slightly from generation to generation, making you more adapted to changes on the planet Earth. Since there are cosmic radiations raining down us even as we speak, it means that our genes are being altered every day by impacts from subatomic particles, meaning that we can adapt to changing conditions because cosmic rays give us a cosmic roll of the dice which changes our genetic makeup.
Cosmic rays can also cause bad mutations that can lead to cancer.
The good news is that even though there are thousands of cosmic rays passing through our bodies every second, they're so tiny that the likelihood that they'll hit right on a spot of DNA that disrupts that nucleus and makes that cell cancerous is very, very, very small. But if you're in an environment like the astronauts face, where you have a lot of radiation, very little shielding, then you can start to accumulate some risk of being hurt by the radiation.
Passengers on transpolar flights also may be at risk of increased radiation exposure from cosmic rays.
In fact, some of the crew members on transatlantic, transpolar flights will actually wear little radiation badges, and they actually discourage pregnant women from being stewardesses or pilots on those particular flights because they're worried about it, and they haven't demonstrated that it's actually an effect, but they are very careful about those radiation levels.
Cosmic rays not only make an impact on all living organisms, they also may influence the weather.
There are some theories that galactic cosmic rays may be part of the initiation of thunderstorms. actual lightning strikes because they can cause an ionization path through the atmosphere that might just open up the path that's needed for the lightning bolt to start.
We've all seen lightning during a thunderstorm, but as scary and spectacular as these deadly bolts can be, they're literally on the low end of related phenomena, known as transient luminous events that take place in the upper atmosphere. Thanks to advances in high-speed video cameras, we've been able to verify their existence. One of them is called a sprite. This jellyfish-shaped flash of light appears about 45 miles above the Earth's surface and lasts only a few milliseconds.
Sprites are an interesting electrical discharge that can go up to something like 55 or even 60 miles in some cases, but it can also go down to an altitude of maybe 30 miles above the Earth's surface. So you have these two streams of electricity going both up and down, and it sometimes has a reddish-orange hue. That's caused by excitation of neutral nitrogen molecules in the atmosphere.
Another recently discovered phenomenon is elves. No, they're not imaginary figures of folklore. Rather, it's an acronym for a very long explanation of the process that generates these glowing bursts of energy around 250 miles in diameter. Ready? ELVS stands for emissions of light and very low frequency perturbatons from electromagnetic pulse sources.
ELVS are actually kind of a relative of sprites. The one difference between ELVS and sprites is that ELVS will actually last for even a shorter amount of time. So the only way to see an ELV is to have a very sophisticated camera, and would have to probably catch it by accident. The ELVs are not visible by the naked eye because it's such a short burst of energy.
Closer to Earth, other distinctive discharges occur, known as blue jets.
Blue jets start from just above the tops of the thunderclouds at an altitude about 10 miles above Earth's surface, and they go upwards to an altitude about 30 miles above the Earth's surface. And usually it's sort of a blue cone-like jet of light. And the blue color comes from neutral and ionized nitrogen molecules that have been excited by this electrical current coming through.
As relatively newly discovered phenomena, blue jets, ELVs, and sprites aren't fully understood. The impact they have on the Earth's atmosphere continues to be a source of ongoing speculation.
There are some theories that it would actually serve to balance out the electromagnetic forces of the Earth, that the ELVs may be associated with producing more ozone. One very simple way to look at it is that nature is constantly trying to balance itself out, and because of that, there are eventual benefits to life on Earth.
Cosmic phenomena not only affect the weather, but also plants and animals. Without their interactions with the sun, our lives would be thrown into chaos. The sun acts like a cosmic alarm clock, regulating our lives. We measure our days in sunrises and sunsets. The same with plants. The most delicate flower to the tallest tree relies on this cosmic force to tell it what to do.
One great example of that is flowering. Some plants are short day, some plants are long day. The long day plants can sense the lengthening of the sun, of the day that happens in spring. The short day plants feel the shortening of the sun towards the winter. So chrysanthemums, for example, are short day plants. They flower in the fall. Petunias or marigolds, those are long day plants. They flower when daylight is getting longer. This is all due to mechanisms and chemical compounds in the plant that can detect the time that the sun is out there.
Telling plants when to flower is just one way the sun plays a key role in their lives. Another way is the role the sun plays in initiating a process called photosynthesis. Without this cosmic interaction, plants would die, and so would we.
Photosynthesis is just like solar cells. Basically, the plant takes sun energy and turns it into a form of energy it can use to grow.
Chlorophyll, the green pigment in leaves, allows plants to absorb sunlight and begin photosynthesis.
Chlorophyll is a huge molecule of magnesium surrounded by smaller molecules of carbon, and they all kind of support it. And what this molecule does is it takes light energy and absorbs it for things the plant can use.
Photosynthesis triggers a complex process that causes plants to combine carbon dioxide and water to make sugar, which in turn is used to make starch, fats, and proteins, the food we eat. At the same time, plants release oxygen for us to breathe.
If photosynthesis were to quit working, we'd all be dead. That's the bottom line.
That includes animals. Like us, they rely on the sun to provide sustenance, regulate their lives, and just maybe how to navigate their way in the world.
Navigation is very widespread in the animal kingdom. Salmon find their way back to the gravel bed where they were hatched. There are big migrations of caribou. There are huge migrations of grazing animals in Africa. There are insects that migrate. The monarch butterfly, for example, is a spectacular case where the adults that are born here in Ithaca go and spend the winter down in Mexico and then come back. I mean, there are many, many examples of this, and not for a single one of them do we really understand fully the cues that they are using on these long journeys.
Studies offer some clues to the mystery of how animals navigate. Many species use the sun to determine direction.
That's not so easy if you think about it, because in order to use the sun that way, you have to have a clock. That is, you need to know whether it's the morning, the noon, or afternoon because of the apparent movement of the sun. And so animals do in fact have a biological clock, as do we, which gives them the right time of day.
If conditions obscure the sun, some animals switch to the Earth's magnetic field, a force that originates deep in the planet's molten core. It provides not only directional pointers, but also positioning cues. Every place on Earth has a unique magnetic signature. If an animal is sufficiently sensitive, it may be able to use the Earth's magnetic field to figure out where it is in relation to home by monitoring the differences in magnetic fields.
The problem with using the Earth's magnetic field to locate your position is that the Earth's magnetic field changes. It changes from night to day. It changes because of deposits of iron under the surface of the Earth called magnetic anomalies, which distort it. And it also varies because of sunspots, which cause variation in the field. And all of these things means that it's relatively noisy. And yet, it seems, many animals are able to make use of it to find their way.
A training toss of homing pigeons shows how animals may use the sun and the Earth's magnetic field to find their way home.
Homing pigeons have been domesticated for years for this ability to find their way home. They have been raised for generations to be the athletes of the pigeon world, so they fly very long distances.
The first step in a pigeon release is you go out to your loft and you select the pigeons that you're going to use for the training toss that day. And what I look for is I want to make sure all the pigeons are in good physical condition, their feathers are all in perfect condition, and they look like they want to fly. And I'll select those pigeons and I'll put them in what is called a pigeon basket, which is basically a small box that is used to transport the pigeons from their home loft over to their release point. The next step in the pigeon toss is the actual release, where we come out into a field where there are no trees around and it's an open area, and we open the box and let the pigeons go.
Once in flight, the pigeons, experts think, first use the sun to orient themselves, then navigate their way home, probably by using their sense of smell and the Earth's magnetic field.
There are two sense organs that seem to be involved in detecting the Earth's magnetic field. One is in the visual system, in the eye, in the retina of the eye, and the other is in the pigeon's upper beak, the mandible of the beak, where there are a whole bunch of deposits of magnetite, which is a magnetic mineral. And that also seems to be involved in detecting the magnetic field. So there are two sense organs, and we still don't really understand exactly how these interact and how they're used by animals to find their way around.
The last part of a pigeon toss is the return, where the pigeons fly back to their loft and land on the platform and then go back inside.
A simple pigeon toss may show, but doesn't fully explain, how animals use the cosmos to navigate. It's a confounding mystery that may never be completely solved.
It's made very difficult by the fact that animals use several different techniques. And so when you do the usual classical thing of making it hard for them to use the sun, the stinkers switch and use the Earth's magnetic field. And it's this whole business of having a number of different tools in their armory, just as we do in finding our way around, that makes it so very difficult experimentally to unravel exactly what is going on.
Like the magnetic field, there's another cosmic force that affects life on Earth in mysterious ways. It hides in broad daylight, but there's no hiding from it. Ignore it, and you'll get burned, or worse. A cosmic phenomenon gives us that golden tan we crave and that seemingly healthy look. But that look only goes skin deep. A tan is the most common effect from a potentially deadly solar source, UV, or ultraviolet rays.
Ultraviolet is that part of the spectrum that we can't see with our eyes, but there's a fair amount of it out there, and the sun is putting it out all of the time. Now, just like there are colors in the visible spectrum, there are colors of ultraviolet, depending upon what the wavelength is, and we've divided them into 3 different bands: ultraviolet A, B, and C.
For example, ultraviolet C is blocked almost completely by the ozone layer. Ultraviolet B gets through a little bit more, and ultraviolet A gets through the most because it's the closest to being visible light.
UVA is considered the aging and skin cancer ray, and UVB is considered the burning ray. So the UVB rays cause sunburns, and the UVA rays cause the freckles and the sunspots.
This is a model of a cross-section of skin. When you're outside, the UVB light will go superficial into the skin and cause sunburn. So that will damage the cells that make up our skin, keratinocytes. When the cells are damaged, the body responds by activating the immune system, and that will increase the blood flow to the area of injury, and then it will activate the immune cells to produce small molecules that causes inflammation.
And that's just the beginning. Prolonged exposure to UVB rays from the sun can cause cataracts, and it can also be a factor in skin cancers, such as melanoma, a potentially fatal disease.
The people at most risk of developing skin cancers from sun exposure are the lightest skinned people, the people with the lightest eyes, the people who live in the sun, the people who never wear sunscreen. Those are the most at risk.
There is, however, a bright side to UVB exposure, and that's the production of vitamin D in the skin.
We can produce vitamin D with an innate molecule that's actually in the skin plus UV radiation, which converts this molecule into vitamin D, which we need for healthy bones, healthy calcium metabolism. However, we can also get that vitamin D from fortified foods and from supplements, so we don't absolutely have to get it from UV radiation.
While UVB interacts with the surface layer of skin, UVA penetrates deeper, adding a new wrinkle to sun exposure.
UVA exposure that goes deep into the lower layer of the skin will lead to photoaging and will break the collagen by increasing enzymes that break up the collagen and the elastic fibers that's in the dermis that gives us the youthful and tight and healthy skin.
Tanning booths try to recreate the sun's rays artificially. But exposure to man-made sun in a booth is worse than lying under the real thing, 93 million miles away.
The tanning booth industry will make you think that tanning booths are safer and the tan you get from laying in them is a safer, more gradual tan, but the opposite is true. In fact, tanning booths are even more harmful to the skin. The reason is because the bulbs are over 90% UVA rays, and those A rays are the aging and skin cancer rays, so people will develop skin cancers 20 and 30 years later. It's a known fact that going to the tanning salon increases your risk of skin cancer.
Many people also think that regular sunscreen will protect them from skin cancer and premature aging. Not true. Not even sunscreens with a high SPF number will prevent these harmful effects from the sun.
SPF is sun protection factor, and it measures how much time you can be out in the sun without getting burned. So SPF factor only measures the UVB protection, not UVA.
The most effective sunscreens provide protection against both UVB and UVA. But even with frequent reapplications, sunscreens are no guarantee against skin cancer, which may be increasing due to the depletion of the ozone layer.
What ozone does is it forms sort of a blanket over us that absorbs a lot of the incoming radiation. So what happens if you lose your ozone, you get more and more of this higher energy radiation, the UVB. And that's the stuff that's bad for causing damage to your skin.
It's interesting to note that 2 billion years ago, before the Earth had an oxygen-rich atmosphere, it had no ozone layer, and life did not exist on the surface of the Earth. It could only exist under the ocean layers where it's protected from ultraviolet light by the water.
While ultraviolet light is invisible and its effects may harm us, the sun's visible light is the source of what may be the most beautiful cosmic effect of all. The sun plays a key role in causing one of the most spectacular light shows of all: rainbows.
Rainbows form when sunlight, which we call white light, passes through spherical droplets. Rain is generally spherical droplets. And the light gets dispersed or spread out into a rainbow of colors because the light bends by different amounts as it goes through the droplet, depending on its color or wavelength.
The red is one extreme, long wavelength. The blue is another extreme, which is a short wavelength. Of course, there are other colors. There's other wavelengths in between that are refracted at different angles. So that's why you get that spectrum of light, because the change in wavelengths is continuous as you go from short up to long wave. A very good analogy to a rainbow can be created with a prism. The sun for the light source, but instead of a raindrop, you now have a prism. Different wavelengths are refracted at different angles. They're refracted twice, once out of each side, and then you have a rainbow that is produced from the separation of red all the way through blue.
different wavelengths of light, refracted or bent at different angles, explains why the colors of the rainbow appear in the order they do, and in that arc-like shape.
There's a certain set of angle where a preponderance of the light is bent, and so it collects up there. There's a certain angle where there are more rays than at other angles because depending on the angle of incidence of the sunlight, more rays tend to bunch up in this particular direction.
That angle is 42 degrees from the anti-solar point, a fancy astronomical term for the shadow of your head. At that angle, the incoming light is at its most intense and where the rainbow appears. But 42 degrees from the shadow of your head is different than 42 degrees from the shadow of someone else's head. This means no two people see the exact same rainbow. Sometimes, if you're really lucky, or at least standing at the right angle, you'll see a secondary rainbow.
What happens inside the raindrop, where you have this diffraction, sometimes it bounces more than once. And so when it bounces a second time, it comes out at a different angle, it's a larger angle.
51 degrees to be exact.
And it'll be dimmer because most of the light escapes after the first bounce, but some of it goes in the second bounce. Now the interesting thing about the second rainbow is it's in the opposite order. So the red that's on one side on one rainbow will be on the opposite side on the other.
Whether in single or double form, a rainbow doesn't appear at a fixed point in the sky. Its apparent existence depends solely on the observer's location and the position of the sun. In this light, a rainbow may be viewed as an optical illusion.
In some ways, a rainbow is an illusion. You can't walk to a rainbow and touch it or pick it up. It always maintains its distance away from you. Because the rainbow really just is a set of light rays coming toward your eye from a set of angles. And as long as there are droplets in those directions, you will see a rainbow. But if you go to where the droplets are, you've changed the angle and the rainbow disappears. So really, in that sense, a rainbow is an illusion.
The rainbow's simple beauty and complex science have imbued it with legend. The ancient Greeks considered it a path between their gods and the earth. The Irish leprechaun's hiding place for his pot of gold is said to be at the end of a rainbow, a place impossible to reach. And the Hindus believed it was the bow belonging to their god of lightning and thunder. The beauty of a rainbow, the complexity of photosynthesis, the impact of UV rays, the mystique of an aurora. These diverse cosmic phenomena all shed light on our relationship with the universe.
We are anything but passive bystanders in this whole pageant of phenomena that we see between Earth and space. Life on Earth evolved in this environment of cosmic rays and aurorae and lightning, and all of the kinds of phenomena that we see is just part of the environment in which we evolved. And so it is part of us, and we are part of it.
The beautiful atmospheric phenomena that we see, rainbows and auroras and meteors flying by, as well as the potentially harmful things like UV radiation from the sun, show us the Earth is not just some isolated sphere detached from the rest of the universe. No, we're part of it. And that makes the Earth all the more beautiful.